Hello friends, welcome to Ally Learn. Today, in this lecture, we will study the Cauchy problem for a first order quasi-linear PDE. So friends, let's first of all see what is a Cauchy problem. So for that, just try to recall your initial value problem in ordinary differential equations. There, what you used to do, you used to find a solution of the ordinary differential equation, and then you had an initial value at an point. Okay, you were given a value of the function at some point, and using that point you used to eliminate that constant and then get a solution of that ordinary differential equation satisfying the initial conditions. Something similar we will be doing over here to quasi-linear PDEs. So, the Cauchy problem is to determine a solution of the first order quasi-linear PDE given by this equation. This equation is the equation of first order quasi-linear PDE. Now, what we have to do in Cauchy problem is that we have to find a solution of this first order quasi-linear PDE satisfying some initial condition, and that initial condition we will tell you. So, what we have to do, we have to find a solution of this equation in a neighborhood of a curve C such that the solution takes a prescribed value, say z0 on C. So let's come again. In the Cauchy problem, we have to first of all find the general solution of this first order quasi-linear PDE and then use these initial conditions to get rid of the arbitrary function that we get in the general solution of the first order quasi-linear PDE. And this curve C will be called the initial curve of the problem, and this value z0 will be called the initial data or the Cauchy data. And since in the previous lectures we have seen that solutions to PDE are surfaces called integral surfaces. So Cauchy problem is to find integral surfaces of PDE containing a given initial curve. So friends, now just focus on this last line, that is, Cauchy problem is to find integral surface of PDE containing a given initial curve. So just try to recall friends that solutions, in particular the general solutions of first order quasi-linear PDE contains an arbitrary function, and for every such function we get a solution surface. So in Cauchy problem, what we do, we consider that surface solution that contains the given curve C. Okay, in Cauchy problem we select that surface that contains the given curve C. So what we are doing, we are giving that arbitrary function a particular value. Okay friends, so again I repeat, what we do in the Cauchy problem, we have a first order quasi-linear PDE. We find its general solution, and that general solution contains an arbitrary function, and solutions to first order quasi-linear PDEs are surfaces. So for every such function we have a solution surface. Okay, but here in the Cauchy problem we look for that surface that contains the given initial curve C. We want to find that surface that contains this curve C. So what will happen? that arbitrary function will have a particular value. So this is what happens in a Cauchy problem. So it is very similar to your initial value problems of ordinary differential equations. There you used to find the solution of an ordinary differential equation and satisfying an initial condition, and with the help of the initial condition you used to find the value of the arbitrary constant. And similar thing happens in this Cauchy problem. What you do? First of all, you find the solution surface of the quasi-linear PDE, and then using the initial conditions, you find the value of the arbitrary function, making it a particular function. Okay friends, so now let's move on to the method of the Cauchy problem. So now we come to the Cauchy problem method. So first of all, consider the quasi-linear PDE, which is of this form, and the Cauchy data as this. Now this is the equation of the initial curve C. We want to find general solution of this quasi-linear PDE containing this curve C. Okay friends, so you must have noticed one thing, that I am again and again saying that we have to find a solution. Okay, and you all know that in order to find the general solution of a quasi-linear PDE, we have to use the Lagrange's method. So our first step is to find the general solution using Lagrange's method. And you must be remembering that in order to find the general solution using Lagrange's method, first of all, we have to consider the Lagrange subsidiary equations, which are these, and then we find the general solution, which is an expression of this type: a function of phi and psi equals 0, where phi equals to c1 and psi equal to c2 are the solution curves of these Lagrange's subsidiary equations, and this f is an arbitrary function. Okay friends, so this was my first step, which is very simple because we have already covered this first step in previous lectures. We have seen how to find the general solution of quasi-linear PDE using Lagrange's method. So after finding the general solution using Lagrange's method, the next step will be to put this initial data, or you can call it Cauchy data, in the general solution and then get the value of this arbitrary function f. And then the resulting expression will be the solution of this quasi-linear PDE containing this initial curve. Okay friends, so now let's move on to our second step. Second step, as I already told you, is to put the initial data or the Cauchy data given by tau in the general solution given by these expressions: phi is equal to c1, psi equals to c2, and f of phi psi equals 0. So now friends, only one thing that I told you is remaining, that is to put this initial Cauchy data in this expression to get a particular value of this function f. Now friends, there are two ways to deal with this type of question. First of all, you can put the Cauchy data over here in this expression and get the value of this function f. But this in some cases involves some complicated calculations. So instead of this, we will be using an easier approach, that is, we will be using this expression to get a relation between C1 and C2 and hence connect phi and psi by a relation, and that relation will be solution to the Cauchy problem. So what we'll be doing, we will be finding a relation between phi, and psi using the Cauchy data. This, what it will do, it will eliminate the arbitrary function f by finding its particular value using the initial or the Cauchy data. So, when we find a relation between phi and psi, that relation will be same as the relation obtained by putting the Cauchy data in this expression and finding a particular value of f. But because that will involve some complex calculations, so we will be considering this expression only. We will be putting the Cauchy data over here to find a relation between C1 and C2, and that relation will also connect phi and psi, and that will be our solution to the Cauchy problem. So friends, now let's move on to a question and apply this method. So the question is, find the solution of the first order quasi-linear PDE given by this expression. U into x plus y, this is partial derivative with respect to x, plus u into x minus y, this is partial derivative with respect to y, equals x square plus y square. Now this is the quasi-linear PDE, and the Cauchy data is given by this expression u equal to 0 on y equals to 2x. So friends, what we have to do, we have to find a solution surface of this quasi-linear PDE containing the curve y equal to 2x, and value of the function is 0 on that curve. Okay, it's like suppose I have to find the solution surface containing this curve C, and this C curve is y equal to 2x, and on this curve the value of u equals 0. Okay friends, so now let's start with the solution. First of all, we have to find the general solution of that first order quasi-linear PDE, and the general solution we find by the Lagrange's method. So friends, this question we have also done in our previous lectures. We have found the general solution of this quasi-linear PDE using Lagrange's method in our previous lecture on Lagrange's method. So I will be moving on quickly with these steps, but these steps are explained in detail in our previous lecture. If required, you can view that lecture. Okay, so I'll be moving little quickly with these steps. So first of all, what we do, we form the Lagrange subsidiary equations, and these are these. Okay, so this is dx upon the coefficient of ux, dy upon the coefficient of uy, du upon the term on the right hand side. Okay, now the next step is to find two linearly independent solutions phi and psi of the Lagrange subsidiary equations. So what we do over here, we choose Lagrange multipliers as L equals x, m equals minus y, n equals minus u. So these are my L, m and n, and this is my capital P, this is my capital Q, and this is my capital R. So now I will be considering LP plus MQ plus NR. I just put the values over here. By taking the terms inside the bracket we get this, and opening the bracket we get this, and just cancelling out the terms, this and this one with this one, and this term with this one, we get this to be equal to 0. Now consider this ratio LDX plus MDY plus NDU over LP plus MQ plus NR. Now you know that this denominator we are getting it to be 0. So the denominator equals 0 implies the numerator has to be 0. So what we get? This numerator equals 0. So we get this expression to be 0, Now we'll put the values of L, M and N and then integrate and get a solution. So what we do, we put the values of L, M and N as x minus y and minus u. Now we put the integration on both the sides. On the right hand side, this c is the constant of integration, and on integrating these expressions we get this expression. Now just manipulating it to make it in a simple form, we do these calculations, and this 2c we are writing as a constant c1, because c is a constant, so c1 equals to 2c is also a constant. Now this is my first solution that I'll be naming as phi. So phi equals x square minus y square minus u square equals to c1 is my first solution. Now I move on to find my second solution. So now again consider the Lagrange characteristic equations. So for the second solution, what we do, we compare the first two ratios. So comparing first two ratios, we get this step. Now we cancel u on both the sides, and now we just cross multiply, and now we open the brackets. Now in this step, after opening the brackets, I get x dx minus y d. This is x, not y. Okay, this is x and not y. What we got? X dx minus y into dx equals x dy plus y into dy. So just make this change over here. This is not y, this is x. After this, what we do? We shift this term to the left hand side and we take this term on the right hand side. Okay, and now we come to this step after taking those terms on the left and right hand side respectively. Now what we do, we take the d common and we get this to be d of x square by 2 minus y square by 2, and here also I take d common, so I get d of xy. What you can see over here is that when you expand this term d of xy, you will get y dx plus x dy, and when you expand this expression, you will get 2x over 2 into dx minus 2y over 2 into dy. That is precisely the expression over here. Fine. So afterwards, you take this term on the left hand side, you get this expression. Now take the common. Now what we do, we integrate both the sides. So what will happen? The integration sign will cancel with this derivative sign. That was the purpose of writing d outside, so that we can easily cancel it with the integration operator. So after applying integration on both the sides, we get this expression where c2 is the constant of integration. Now this is my second solution. I just want to make it in a standard form, so just little bit calculations, and now I get this one. I'm writing this 2c2 as c3, which is again a constant of integration. Now this is my second solution, which I will be naming as psi. So psi equals x square minus y square minus 2xy equals c3 is my second solution. So I have got my both solutions. So now I can write my general solution. So my general solution is f of phi psi, which equals f of x square minus y square minus u square, comma x square minus y square minus 2xy equals 0. So this is my phi, this is my psi. So this is my general solution where f is an arbitrary function. So with this, my first step is over. I got my general solution using the Lagrange's method. Now I move on to my second step, in which I have to put the Cauchy data in this expression in order to get a relation between phi and psi. Or in other words, I have to eliminate or get a particular value of this function f. Here the function f is arbitrary. After putting the Cauchy data, I will get a particular value of f. So now let's move on to our second step, in which we put the Cauchy data in the general solution. So step 2, put the initial data or Cauchy data tau, that is u equals to 0 on y equals to 2x in the general solution. So we have to put this Cauchy data in the general solution we just now obtained. Now this is my general solution where these two were the solution curves. So friends, as I told you earlier that putting the Cauchy data in this expression can make calculations tougher. So we will put the Cauchy data in these two expressions and we will get a relation between C1 and C2, and the same relation will connect x square minus y square minus u square and x square minus y square minus 2xy, that is my phi and psi. Now we will find an expression for an arbitrary point on this curve, and then we will put that arbitrary point in these two equations. So in the curve u equals to 0 on y equals to 2x, we take x equals to t. Then what will be my y? Then y, which is 2x, becomes 2t, and u is given to be 0 on this curve, so u remains to be 0. So t, 2t, 0 is an arbitrary point on the initial curve tau. Okay friends, so what I did, I took any value of x, then I found the value of y using this equation, and u was given to be 0. So t, 2t, 0 is an arbitrary point on the given initial curve. Now, since the general solution contains the initial curve, so this point also satisfies the general solution. This is an arbitrary point on the initial curve, and the general solution contains the initial curve, so this point also satisfies the general solution. So as you have seen that this arbitrary point also satisfies the general solution, so now we will put this point in this equation phi equals to C1, and in this equation psi equals C2, as these are the solution curves generating the general solution. So first of all, we put this point in phi equals to C1. So what we get over here, this equals C1, we put x as t, y as 2t, and u as 0. Now we do a bit of calculations. T square minus 4t square equals C1 minus 3t square equals C1. So we get t square equals minus C1 upon 3. Now we put this point in psi equals C2. So now put x equals t, y is equal to 2t, again x equal to t and y is equal to 2t. Now do a bit of calculations. We get t square minus 4t square equals c2. So this will give me minus 7t square equals c2, and finally I get t square equals minus c2 over 7. Now friends, just look at it little bit carefully, that these two expressions, this one and this one, what is happening here now, these two are equal because each of them is equals t square. Okay, t square equals this expression and t square equals this expression. So what I get that minus C1 over 3 equals minus C2 over 7. So this is my connecting relation which connects C1 and C2. So let's look at it again. From the previous two equations, what we get that minus C1 over 3 equals T square, which also equals minus C2 over 7. So my relation containing C1 and C2 is this one, minus C1 over 3 equals minus C2 over 7. So just cross multiply, we get this expression. Take this term on the left hand side, we get this expression. Now, as you must be remembering that I had my phi equals C1 and psi equals C2. Okay, so what I am doing next is I am putting, instead of C1 I am putting phi, and instead of C2 I will put psi. So after putting phi instead of C1 and psi instead of C2, I get this expression. So this was my phi, that was my first solution of the Lagrange subsidiary equations, and this psi was my second solution of the Lagrange subsidiary equations. Now we have to do just a little bit of calculations. Take 7 and 3 inside the brackets, we get this expression. Now we just combine the like terms, 7x square and 3x square, 7y square and 3y square, and write the remaining two as it is, and we get this as 4x square minus 4y square plus 6xy minus 7u square equals 0. Now I take just take few terms here, and then I get this expression that 7u square equals this thing. I just put 7u square over there, and then I interchange LHS and RHS to get this equation number 8. Now this equation 8 I got by putting the Cauchy data in phi equal to C1 and psi equal to C2, and then by few calculations I got this relation, and then the relation containing C1 and C2, and then I put the values of C1 as phi and C2 as psi to get this expression, and then with a little bit of calculations I got final equation number 8. Now this equation number 8 I obtained by putting the Cauchy data in the general solution. Okay, and now this equation contains no arbitrary function, neither any arbitrary constants C1 and C2. So this is my solution of the Cauchy problem. This I obtained by, first of all, I got the general solution of the given quasi-linear PDE by Lagrange's method, and then I put the Cauchy data in the general solution, and then I got the connecting relation between C1 and C2, and afterwards I put the value of phi and psi instead of C1 and C2 to get this solution. So the solution of given Cauchy problem is 7u square equals 4x square minus y square plus 6xy. So this is the solution surface of the given quasi-linear PDE that contains the curve u equals to 0 on y equals 2x. You can verify by putting y is equal to 2x in this expression, you will get u equals 0. Okay, so with this we come to the end of this question. With this we come to the end of our today's lecture. Thank you for viewing this lecture. do visit our site alilearn.com and do provide us your useful feedback and suggestions. Thank you.